Okay, so in this video, we're going to try to cover just the essentials of organic chemistry which pertain to AP chemistry. So what would that include? Let's see, what would our objectives be? Well, there are actually no direct organic chemistry objectives in AP chemistry. However, the questions in AP chemistry are often going to use organic compounds to illustrate the concepts that we do need to know. And so it's good for us to be familiar with some of the basics of organic chemistry. So let's start by introducing what organic chemistry really is. It's the study of carbon compounds and their reactions. And this slightly disturbing caricature here of a carbon atom, I can't really tell where its mouth is, but it has four hands. And that's because carbon can form four bonds. And that makes it very versatile. So we'll look later at some of the common bonding patterns that carbon exhibits, and we'll see that that really allows it to form just a great variety of compounds, just millions and millions. Now, why do we call carbon chemistry organic chemistry? Well, certainly a lot of biochemical molecules or molecules that you'd find in life forms contain carbon. And there used to be a belief that most biological compounds needed a vital force to create them, and they couldn't be synthesized in a lab. This notion known as vitalism, or this philosophy known as vitalism, was disrupted especially when a chemist named Wöhler in 1828 successfully synthesized urea, which was an organic compound people were familiar with. And he did that just by decomposing ammonium cyanide. And a couple of other experiments started to erode this perception that organic compounds, or those that are characteristically found um, in organisms, uh, this idea started to be eroded by this and other experiments involving electricity and frogs' legs, which we'll talk about a little bit later in the year. So, we care about organic chemistry because it's so important in biochemistry, and of course, it makes sense that pharmaceutical industry is going to be concerned with organic chemistry more so than inorganic chemistry often. And this is how we make polymers and plastics. Those are organic compounds, and explosives and fuels. And so there's lots and lots of important applications of organic chemistry. Here's a picture of acetyl salicylic acid, which is aspirin. We've done some labs with that before in first year chem. But you might not recognize the way it's represented there. Let's talk about this funny way of representing organic molecules called a line diagram, also known as a skeletal formula. In the bottom of this slide, you'll see there are four different ways of depicting propane, actually five if you count this model here. The first one is the Lewis structure that we're familiar with, and instead of drawing the bonds as lines, they're just drawn as dots here. But if you drew them as lines, you'll see since this Lewis structure has no lone pairs, then the structural formula is essentially a Lewis structure. But if you picture the model for this, there it is, CH3, CH2, CH3. That's what we'd call the condensed formula as you read it left to right. Then essentially you'll notice there's this carbon backbone. And that's what a skeletal formula tries to draw, is just the carbon backbone. And all of the bonds to hydrogen are implied, and only the carbon atoms are implied by either an end of a line or a bend in the line. So let's talk about interpreting these skeletal formulas. This would be an example of a skeletal formula with 1, 2, 3, 4, 5 carbon atoms in a chain. And if I rotate this molecule so I'm looking at it in a top view, then it might look like they're all in a line. But in the side view, you can see since each of those carbon atoms has tetrahedral geometry, there are actually 109.5 degree bond angles between carbons, not the 180 degree bond angles between carbon, 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 like is implied here. So it might be helpful to look at a model for a moment. This is propane once again, and you can see if I rotate it so that it's oriented in this direction, it may look like the Lewis structure we would draw. But if I rotate it in this direction, you can see that the bond angles are made more clear. Here's the skeletal formula that's being drawn to represent just the carbon backbone. And those are an important, that's an important way of representing organic compounds that we may need to interpret. Here we have, 3, 6, 7 carbon atoms in a row, and you can see how it's essentially drawn just the carbon backbone. It looks like a couple of W's strung together. We need to know that the end or bend in a line is always going to represent a carbon atom, and we assume carbon always forms 4 bonds, and everything else is assumed to be hydrogen unless it is otherwise marked. So here's a nice summary of interpreting line diagrams. First of all, any bond from carbon to hydrogen does not need to be specified. So here I see a carbon, since this is a bend or an end of a line, and I see 1, 2, 3 bonds specified. That means there must be 1 bond to hydrogen implied. The carbon atoms themselves are not specified. This is a bend in a line, so that's a carbon atom. This is a carbon atom, and so on. There's a single bond between carbon atoms. If a carbon atom is bonded to something other than carbon, we need to specify that element. So here's a double bond to oxygen. It's also helpful to know that lone pairs will often be omitted from these line diagrams. And if carbon is bonded to, if hydrogen is bonded to something other than carbon, then we need to specify those bonds to hydrogen. Sometimes you'll see these dash and wedge conventions, which are used to show three-dimensional geometry. And if you look at all the other carbon atoms implied in this skeletal formula, they all are trigonal planar. So here, 3 domains. Here, 3 domains. That means this whole part of the molecule is really planar. And so is this. However, there is tetrahedral geometry around this carbon, and for that reason, we show this as a 3-dimensional part of the structure. Organic compounds can be represented other ways as well. And you may see a whole bunch of different styles in representing organic molecules, but once you start to think about skeletal formulas, these become a little easier to interpret. In this case, we have a carbon atom here and a carbon atom here, tetrahedral geometry around each, and the red part of the line here is representing an oxygen atom at this location. We'll learn later that this is a model of ethanol. Here's a rather complex one, and here's an extremely complex biomolecule, probably a protein, and it's showing how versatile carbon is in making these really large, complex molecules. So hopefully we can interpret skeletal diagrams or line diagrams. Let's talk about the common bonding patterns that we observe for carbon. Since it usually has 4 bonds, we're either going to see this tetrahedral arrangement, which we've learned is sp3 hybridized, or this trigonal planar arrangement, which we've learned results when carbon is sp2 hybridized, 3 domains, 120-degree bond angles, or here the linear geometry that results when carbon has a single and a triple bond, or 2 double bonds would also give us a linear arrangement that's sp hybridized carbon. So because carbon has 4 valence electrons, it tends to form 4 bonds. That means it can do a lot of things. It can form straight chains, like a whole bunch of carbon atoms in a row. Branch chains, where we take one string of carbon atoms and build it off another. We can even wrap it around in a circle and have one end of this chain connect back to the beginning. And we get what are called cyclic or cycloalkanes. We can not only do that, but we can form single bonds, double bonds, or triple bonds. So you can imagine why there's just hundreds of millions of organic compounds that we can make. We'll start by just classifying the very simplest type of hydrocarbon, or the simplest type of organic compound called a hydrocarbon. In other words, hydrocarbons are compounds which only contain carbon and hydrogen. It's helpful to note that the carbon-hydrogen bond is not a polar bond, and that's going to help us when we're evaluating the types of intermolecular forces that can exist between hydrocarbon molecules. But hydrocarbons, of course, include things like propane and butane, and these are flammable compounds, and they typically are insoluble in water. And I put an asterisk next to that because for every rule there's an exception, but typically these are not going to be soluble in water because they're not going to be capable of forming strong intermolecular forces with water. Here's an example of some hydrocarbons. The two subclasses of hydrocarbons include what we call saturated hydrocarbons and unsaturated hydrocarbons. Now, saturated hydrocarbons have single bonds only. Why would we call that saturated? Well, it essentially means saturated with hydrogen. Notice if I wanted to put a double bond here instead, then that means there would be fewer hydrogens in the compound, like are here or here. So we call those unsaturated because there are generally fewer hydrogens. We don't need to dive too deep into classifying organic compounds, but it is helpful for us to recognize these three classes of hydrocarbons. Alkanes, like propane and methane and butane. Alkenes, like ethene or propylene, and alkynes, which have triple bonds. So notice alkanes, alkenes, and alkynes are going to be named with these suffixes because they contain single carbon-carbon bonds only, or some double carbon-carbon bonds, or if they contain some triple carbon-carbon bonds, they'll be often named with the "-ine" suffix. And then finally, we'll look at a few ring structures, which are often called aromatic hydrocarbons because they often are ones that we can sense with our sense of smell. So we'll just quickly review the prefixes that are used to name organic compounds. We don't need to memorize these prefixes, but it's not a bad idea to be familiar with them. So you can see the prefixes meth, eth, prop, and bute are kind of unique to organic chemistry. But once we start getting to 5, 6, 7, 8, then you'll start to see those familiar Greek prefixes that we also use for other covalent compounds. Methane, ethane, propane, and butane are the names of the alkanes, single bonds only, which contain 1 carbon, 2 carbons, 3 carbons, and 4 carbons in that order. We'll also hear prefixes or these same prefixes used when we're talking about what we'll call alkyl groups. And an alkyl group is essentially when you have just a branch chain or something branching off of the main part of the organic compound. If it's just 1 carbon that branches off, we'd call that a methyl group. If it's a 2 carbon chain branching off, we'd call that an ethyl group. If it's a 3 carbon chain, a propyl group, and so on. So you'll hear these suffixes sometimes as well. Now, naming organic compounds is a pretty complex field of study. But it's kind of fun to play around with, but it's maybe just good for us to look at 2 examples before we move on. We saw these before, and I'm going to count the number of carbons, 1, 2, 3, 4, 5. Because this is an alkane, only single bonds, with 5 carbons, it is named pentane. Because this is an alkane with 7 carbons, we'd call that heptane. And there are all sorts of variations we can consider, and even things called structural isomers we'll look at later, but it's helpful to at least be familiar with how these prefixes are used. So hopefully we can see how these line diagrams, ball and stick models, or Lewis structures are all kind of representing the same thing, but these sure are easier to draw. So sometimes you may see line diagrams or skeletal formulas, and we should be able to interpret those. And again, to review our 3 main classes of hydrocarbons: alkanes, single bonds only; alkenes, double bonds, and you can see here the bond angles and geometries associated with each of these that I mentioned before. And then finally, here's an example of a cyclic hydrocarbon. And we've actually looked at this before when we looked at this benzene ring, which has alternating single and double bonds. And we talked about the fact that really 2 resonance structures would be needed to represent this benzene ring. And that's because we're talking about sigma and pi bonds being involved. And we looked at this model, I think, earlier as well to show that delocalization of those pi bonds above and below the plane of the sigma bond. And that's going to give us a really common precursor to a lot of organic chemistry labs, which is benzene. And benzene is a liquid that is just an important and really commonly encountered organic compound. Benzene has double bonds in it, although sometimes you can make a 6-carbon ring with all single bonds. That would be called cyclohexane. If there's 5 carbons in a ring with single bonds, that's cyclopentane, and so on. So these are cyclic or aromatic compounds when you get these ring structures. And you can start putting many different rings together and you start getting these multi-cyclic organic compounds. And it's helpful to consider how many organic compounds are going to have this sort of structural feature. Naphthalene is also known as mothballs, and this is basically 2 benzene rings linked together. You can see this circle that's drawn here is a lazy chemist's way of drawing those alternating double bonds. So instead of drawing 2 resonance structures for the double bonds being on the number 1, 3, and 5 carbons, and then on the 2, 4, and 6 carbons, they've just drawn a circle here to represent the model I just showed. If there is a benzene ring with a methyl group off to the end, that's called toluene, also known as methylbenzene, a very, very important precursor or reactant in organic chemistry. Now, let's just briefly talk about how many biochemical compounds are multicyclic alkanes. Here's testosterone and a type of estrogen, and they're very, very similar in their structure. Here's an example of a nucleic acid, and you can see there's some elements of a cyclic compound there. Amino acids, there are many of them, but they also have this recognizable benzene ring as part of their structure. So it is true that organic chemistry is fundamental to biochemistry, whether we're talking about hormones or DNA or amino acids. Here's an example of ibuprofen. Of course, the pharmaceuticals are going to often include these organic compounds as well. So we've learned about structural formulas and how skeletal formulas may be a really helpful way to represent compounds. Skeletal formulas or line diagrams, you should be able to interpret those just as easily as you interpret a chemical formula or a structural formula. The ends and bends are carbon atoms, so this is showing 1, 2, 3, 4 carbon atoms. But if there were something other than carbon, I would need to draw a line to that other element and label that other element. So make sure you're able to count how many carbon atoms are in a structure, for instance, like this one here. This is called an ether, and I see 1, 2 carbon atoms. But this is otherwise marked as oxygen, so 3, 4 carbon atoms are shown in all in this skeletal formula. This would be called diethyl ether. Now, there are a couple of important functional groups here that we're going to talk about, and while many of these are really more complex than we need to consider in AP chemistry, it's going to be helpful for us to just be familiar with the idea of functional groups and talk about a few of these so that we can recognize them readily. So let's wrap things up by talking about a couple of these functional groups which are important to be familiar with. The first one we'll talk about is the alcohol functional group. So looking at this example, we should be able to first of all identify that's 1 carbon, 2 carbons, 3 carbons, and then this is not a carbon, it's otherwise marked. And so this would be 1, 2, 3 is the prefix prop. So this is propanol. And you'll notice alcohols are going to be named things like ethanol, propanol, pentanol, and so on because they have that OH group at the end. Alcohols are the first type of organic molecule we should be familiar with. And there's methanol and ethanol and propanol, which can be isopropanol if the alcohol group is on the number 2 carbon, or it can be 1-propanol if it's on the first carbon. And those are different isomers of propanol. The thing that identifies an alcohol is the OH group on a carbon atom. Please note that the OH group is not a hydroxide anion. This is not going to be a cation bonded with a hydroxide anion, but rather oxygen covalently bonded with carbon on one of these chains. And it is probably most important for us to just note that this is always going to be a molecule, and alcohol is always going to be a molecule that can form hydrogen bonds. It can form hydrogen bonds with water. It can form hydrogen bonds with itself. And so alcohols are soluble in water, unlike alkanes, which are generally insoluble. How about this second group? Carboxylic acids. These are a huge class of organic acids. So there's a lot of organic acids which have this COOH group on the end. Coo. Now, this is how it's arranged. And so you'll see what is often referred to as the R group, where R is just whatever the carbon chain it's attached to is. And then you'll see in red is that recognizable structure, C with a double bond to O and then a single bond to an OH group. And this hydrogen is the ionizable hydrogen. And if you remember, acids are proton donors or H plus donors, and this is the hydrogen that is ionizable. And so the conjugate base of a carboxylic acid is the COO minus anion, and that's carboxylate. And there are many, many acids that are carboxylic acids, a lot of organic acids. And when we study acid-base chemistry in more detail, we'll probably be reminded of this important group of organic compounds. There are also, of course, organic bases. And the most common organic bases are amines. If you think about how we already are familiar with the ammonium cation and how its conjugate base is ammonia, NH3. So ammonium is NH4 plus and ammonia is NH3. That's, again, an example of a hydrogen ion or a proton on NH4 being lost and then rendering a base, the NH3 molecule. And if instead of NH3, one of those hydrogens is replaced by a carbon or another R group, so to speak, then you have this NH2 group on the end. The lone pair on that nitrogen atom is going to attract protons, and that's why amines, anything that has an NH2 group, can act like a base. This is a huge group of organic bases, and a lot of the time when we study acid-base chemistry, we'll be thinking about amines, which are proton acceptors, and when they accept a proton, then they will often become something that ends in NH3 plus because they have gained that hydrogen and the positive charge associated with it. So those are all very important functional groups for us to be familiar with. And you can see there's many, many more. Good questions to consider might be, what's the hybridization on this carbon? What's the molecular geometry around this oxygen? Is this a polar molecule? Which of these in this group here, in this middle column, are capable of hydrogen bonding, and which are not capable of hydrogen bonding? Those are important questions that AP Chemistry will often use organic compounds to illustrate. So here's the last 2 points that I wanted to make in this video. One is that molecules like butane and many other organic compounds can exist in many different isomers. So for instance, both of these isomers of butane have the formula C4H10. However, here it's 4 carbons in a chain, whereas here it's sort of a chain of 3 with a methyl group off to the side. Those both have the same empirical formula, but they have a different structure. And sometimes you might be asked to consider 2 different isomers of a molecule to think about how their intermolecular forces might vary. Another really important point to make is the relationship between intermolecular forces and boiling points is often going to be illustrated using organic compounds. A lot of intermolecular force concepts can be illustrated with organic compounds. Notice as we go from methane to ethane to propane, the number of carbon atoms is going to be increasing. And since all of these are just alkanes, in other words, just carbon and hydrogen, nothing else, they're nonpolar. And the only intermolecular force that can operate are London dispersion forces. So why is the boiling point increasing as we get a larger and larger carbon chain? It doesn't really have to do with molar mass. It has to do with the size of the molecule and the polarizability of the electron cloud. So this is just another example of how some of these AP chemistry topics are illustrated well with organic compounds. And the point about isomers also comes up here. You'll notice we don't start seeing isomers for alkanes until we start getting into more and more carbon atoms, but you can see if we have a chain, if we have this empirical formula C10H22, there's actually 75 different ways we can put 10 carbons and 22 hydrogens together. And one of my favorite images here, which is actually, if I remember correctly, an art installation that exists somewhere in the world, is this image of all of the structural isomers of the compound with formula C6H6. And of course, C6H6 is benzene, and we learned what a benzene ring was, but there's a lot of other ways of putting 6 carbons and 6 hydrogens together. So a pretty amazing versatility for carbon. So that's a crash course in organic chemistry for AP chemistry.